one of the things that is difficult to study is groundwater. And the reason is it's underground and it's really hard. And we can drill a well and sort of see what's going on, but we might not get representative. There's a lot of different words that are used to describe the different parts of the groundwater. And we'll go through these now. So the first one is the top of the groundwater is called the water table, right? That's where the top of the completely all the spaces are filled between the sediment are filled. There's a little bit of water that creeps up and moistens the soil above that, and that's called the capillary fringe, and that's caused by capillary action, which is caused by what causes capillary action to occur?
Wind.
No.
Oh, I guess not underground.
Hydrogen bonds.
Hydrogen bonding, exactly right. That's what causes things to crawl up the edge, right?
In horticulture, we learn it as like how a straw works when you just dip it in and it crawls up the straw.
Exactly. If you have a really fine glass tube, it'll go way up, right? Just pull itself right up. So there's capillary action that allows that. So this is going to be habitat, right, for microbes that maybe couldn't, or other organisms that couldn't live in this unsaturated zone where there is air spaces, and this is called the vadose, or unsaturated zone. If we have an even amount of substrate, the aquifer is called unconsolidated, and if it's not bounded on the top and the bottom, it's unconfined as well. So each of these darker gray things are impermeable layers. You can imagine a situation where we have some impermeable layers that are like big old rocks or something down below there, right? So this makes an aquifer heterogeneous instead of a homogeneous where everything's got, so this could be all sand, right? And this could be big boulders with sand around it. And if you have a sort of a dish up here, you can get what's called a perched water table. So these kinds of things are fairly common in this karst landscape that we're in now.
What makes if it's like you're saying that the little area is like a sandy and rocky, in my mind I'm like, oh, that makes it extra permeable.
If these are really big rocks that are impermeable, the rocks themselves are not permeable.
Okay, it's not like gravel. Okay.
No, the gravel would be quite permeable, but like, let's say giant boulders, like really big boulders or something like that. Yeah, or clay lenses. These could be big blobs of clay, which are not very permeable. It seals up, so that could be, that's another possibility.
Okay, and I don't know if my next question like matters, but I was the table 2 times ago, it talked about subsurface flow, being able to flow. It had an arrow of it going into the ocean. So are you saying the underground water pushes itself into the ocean?
Let me defer that question. There's a figure coming up in a slide or two that will really explain that to you.
Okay, cool.
Right? Okay, and so then the last one is a confined aquifer. If there's 2 impermeable layers, then it's a confined aquifer. So let's start with your question. If there's an input here and then somewhere down here it cuts out, like there's a big valley or something, then this would be flowing from the input to the valley. So you'll see that in a sec. Okay, so here's a question of the day for y'all. If there's a water-soluble pollutant spill into groundwater, would it be more difficult to clean a homogeneous or a heterogeneous aquifer? So to go back, the groundwater spill, there's one here, and there's one here. And you want to do something like pump the water up and clean the toxin out. Which one would, and we can add a little bit, let's say there's also some flow in here, so it's moving. So is it more difficult in the heterogeneous aquifer or the homogeneous aquifer? Good, we're getting a lot of answers. Make sure everyone answers so you get credit for question of the day. All right. Yeah, so everybody got it. Yeah, so you get down here and you know, if there's flow and the pollutant gets down in here and then it then flows through here, but then it flows down there. If you drill down to here, you're not going to see it, right? You're not going to get it. And you're going, it'll be here, but it won't be back here. And maybe it flows down this way, so it won't be here, right? So it does this. Suppose the unconsolidated aquifer, you just get a plume of stuff out here. And you can say, okay, I know where this is. Yes, Lane.
So the water can like move up, right? Would it also take the oil up with it? Or is the oil like have a different, like, since it's not hydrophilic, would it go up with it?
Right. So I didn't specify whether this was a hydrophilic or a hydrophobic compound that was spilled in. So if we had an oil spill, right, the oil would probably sit right up here, right? But if you had a good big enough flow through the groundwater, it might be forced, and then it'll be kind of floating on top, but all up in this stuff, right? So and then if there's like if these are, I don't know, clay particles or something, it'll stick to the clay. So it can be, you know, can be pretty difficult to clean up, and that's why, you know, oil is difficult. But some of them, like, I don't know, atrazine or something, or mercury, which is an ion, it's be just completely dissolved and will go through molecular diffusion or transport, depending upon how fast the flow of groundwater is. It's a good question, and we'll get back to that too when we talk about organics. Okay. So Emma, here's the answer to your question that you had. We have groundwater habitats here, and they are going from all sitting on top of impermeable bedrock, so nothing's going to flow through that. So let's say the water falls up here. The first part, this is limestone, so this is a karst area, right? So there's these different flow areas, maybe some caves, and then a spring coming out. And then we have some kind of like something where sandstone, where water can flow through it, or sandy something. So there's flow here going down. Where the water table here, where the surface of the land goes below the water table, we would have a river or a lake, right? So it's continuous with, this is where the water table is, right? But if you go out of that substrate, for some reason, maybe a glacier cut down here, we get surface water and we get a lake, or if this is a valley, it's flowing towards us, that would be a river there. And then in this case, you have potential energy between here and the ocean, right? So you have water basically can get in the sandstone, and then it can flow through that. In this case, flow all the way out to the ocean.
So it can have higher potential energy than the energy that the ocean seems like something in my mind that's like so heavy. And it seems like once the water got to the ocean line, it'd be like, oh, we can't move any farther.
Well, all that matters is the fact that this surface of water here is higher than this surface of water in the ocean. That's what gives you.
Okay, I see.
Water flows downhill, right? So that's it. You know, we can get in. Will it be more dense or less dense than the ocean if it's fresh water coming in here?
I think more.
Well, you had a
Saltwater.
50% chance.
I forget. Salt water is different. I know that.
Salt water is denser, right, than fresh water. That was a graph. So what will actually happen to this stuff as it pours in is it'll probably work its way up until it mixes with the ocean enough that it becomes equal in salinity. Right. So you can't put fresh water underneath salt water and have it remain stable. Okay, so then we have a water table here, and we have, as we go downhill, right, it's going to be flowing off, so the water table is going to be lower and lower if we go down. So if we have a well in here, right, the well will tell you where the water table level is. So that's how we measure the depth of the water table. So we stick a well in, and then we put a sensor down and say, okay, that's where it is. And we do here. You can drill an artesian well. If you drill, in this case, this well is put down. Okay, so this well here, right, the level here is relative the same as this surface water because we went down here, and the surface water is where the potential is. If we drilled another well down here, let's say we have a stream that's draining water off the water table and lowering the water table on the top, right? But the top of this well is below this potential right here, and the heterogeneous aquifer that's confined right there's where the potential energy is. The water from here is going to come out here because this is lower than here, so it's going to flow. Just think if you have it's like what the toilet is. You open the toilet and it flows down there, and it kind of flows back up into the toilet a little bit, right? It fills it. Okay, so you can have artesian wells or springs that are related to like that.
Was that artesian well just means it's bubbling, like over, spilling over?
Yeah, artesian means the water's coming out. You drill the well and boom, you got water coming out of it.
Okay, so you don't want your toilet doing that.
No, you don't. That's true. Yeah, I mean that's the thing. If you clog it right, then the pressure's on the top and then it overflows. So you don't necessarily want that.
And you just made an artesian well in your bathroom.
Right. And the next thing that happens with wells is that in this case, the groundwater level should be right here, right? But somebody's pumped a lot of water out of this well. So they're actually depleting the groundwater and dropping the level of the water table. Okay, this is what's happening in the High Plains aquifer, the Ogallala aquifer. They're dropping the level of the water table. If you do this near the ocean, this is a big problem near the ocean, is that there's communities like Florida or something where they put wells and they start pulling a bunch of water out of the wells. This level's lower than the ocean level, so the salt water moves in to replace that, and that causes salinity of the groundwater that basically makes it unusable. There's a similar situation that occurs at the city of Wichita because part of their drinking water is from groundwater. It's called the Equus beds. But there's also saline water there that just on the edge of that is left over, essentially salt left over from when this was an ocean. And it dried down and left a bunch of salt. So there's salt mines in the area, but also there's salty groundwater. So when they deplete the groundwater from one area, it's got to fill in from somewhere else. So it's coming in from that salty water. So they have to limit the amount they take out, or the water will be too salty to drink. Right. Doing good here. So large areas of global terrestrial habitats are covered with karst limestone topography. And because that limestone can dissolve, it leads to caves, channels through the water that rivers even can flow in underground, or very small caves. So the Flint Hills is a karst area, but there's layers of limestone and shale. The shale's not permeable and the limestone can dissolve. So we have really small caves, but we get flow of water through that. That's why we've got springs all over the Flint Hills, because they're popping out from those areas of limestone where it can flow through, but it gets stuck on the shale. These lead to really complex flow paths of water, and hydrology, groundwater hydrology is really difficult in this part of the world because of that. Sometimes those caves collapse and it can lead to sinkholes on the surface. And we'll talk about also how these are areas where we can have highly evolved and endemic species. And we already talked about in the field trip yesterday, the Secuidatia tridentata, that's a groundwater invertebrate. These animals tend to lose their pigmentation, they lose their eyes, they don't need them, right? They cost energy to make, and over evolutionary time, they've dropped those out because they can compete better if they don't waste energy making an eye that would never work.
Do the caves that collapse right here, is it way more likely to happen if you're draining the groundwater there?
Yeah, that's a great point. Yes, that's often the major cause of that, because the cave full of water can kind of hold stuff up, but once you get rid of that water, there's no support and it goes in. This is a picture of a sinkhole in Florida. It took a house, and probably related to groundwater depletion, but not necessarily. But You know, sometimes the other thing that's happening is always dissolving, and the cave is getting bigger and bigger and bigger. And at some point, even if it has water and it doesn't have the structure, I mean, even if it does have the water, it'll go. So that's that. So here's the major aquifers of the United States in all kinds of fabulous color, unless you are deficient in your ability to see color. Here is the Ogallala Aquifer, and we'll talk about that in much more detail. One of the big ones for Kansas and Nebraska and parts of Oklahoma and Texas as well. There's some other regional ones, some deep ones, and these are really important in the western U.S. because these are desert areas, right? It's the only water that's available. And this is the ones in Florida. Here's the Everglades, which we'll talk about as well.
If you move to a brand new spot, is there like a website you can go to find out if there's a like groundwater under you, like an aquifer?
Yeah, you definitely can. I mean, people know where the sources of water are, and if it's rural and you need wells, then you basically have to hire somebody to drill a well if you didn't have one, and they know sort of know where it is. They can look for it, but. All right, so Ogallala, High Plains Aquifer, Nebraska to Texas, 30% of the irrigation water used in the United States comes out of that. So a huge amount of our productivity of crops comes out of there. Currently, it's being used about 10 times faster than it's being replaced. And the Arkansas River is an example of one that was fed by this aquifer, but now it's dried out because we've dropped the bottom out from underneath the river. Remember, the water table, the surface of the water table is where the river is, right? Well, if you drop the surface of the water table, then the surface is below where the river channel is, and you don't have a river anymore. Eventually, the deeper the water is, the more it costs to pump up, right? So there's this trade-off with agriculture. If it costs too much to pump the water up to water the crops, then it's not economically feasible. In Kansas, and well, much of the area here, more and more people were not using groundwater and moving over to dryland wheat. Until the gasohol, the tax break for ethanol production came into play. And then corn prices went way up, and it became financially beneficial to a farmer to pump water up and spend the money on the gas, basically, or electricity to pull the groundwater up out. So this is a map of the groundwater, and on the left is the thickness. So it can be up to 1,000 feet thick layer of water in the parts of Nebraska. Many places it's 200 to 400. That's that brownish layer. Some shallow areas. So it's variable deepness, but that's 1,000 feet of water is quite a bit, and even 500 feet deep of water is quite a bit. And then on the right-hand side is the it's from 1999 to 1980, it's the amount of depletion. And this is in level change in feet as well. So these red areas are 50 feet. The water tables drop by 50 feet in these red areas. So there's areas that have been highly exploited. And then in here again, this is probably 20 to 50, more than 50 feet. There's other areas where it's been raining more. And there's actually increases in the depth of the watershed, but mostly it's decreased. And this is the Arkansas River. The Arkansas River at Syracuse, which is the border of Colorado and Kansas, and Dodge City, which is about halfway through south central Kansas. And we go all the way from 1900 here, then there's a break in the records here. And then we go up to almost the present. So what we see is what happened in the 30s that's really important hydrologically.
The Dust Bowl.
Right, the Dust Bowl. So extraordinarily bad drought in this part of the time. And again in the 1950s, extraordinarily bad drought. So we have this plus 0.01. So there's this one place, looks like it dried one time. In that history, right there, and then in the 50s it didn't dry at all. It didn't dry completely. It went down, but it didn't dry. And then it started really drying out and it came up here. Whoops. And this is because Colorado was sued and forced to release water and not use it. But if we look at Dodge City, starting in 1980, center pivot irrigation came in the 60s. So starting about here, and it drove the number down. And now it's a dry channel for almost all the time. It never flows. And that's because the groundwater's dropped out between the Colorado border and Dodge City, the groundwater's dropped out. Now, for functional purposes, the headwaters of the Arkansas River below us, I mean, it goes all the way to the Rockies, but then it dries out. But where it starts flowing again is the Great Bend Sewage Treatment Plant, roughly. So they pump up water and run it through their city system. This is a color image of the state of Kansas and what the drought conditions are in 2006 if you were predicting drought based on the stream flow of the different rivers in Kansas. And the red marks are marks for stream gauges with record low average stream flows for 2006. So all the stream gauges throughout, there's a whole bunch of them. And they also do reservoir levels, so record level low levels. And the brown areas are extreme drought areas based on that. And severe drought is the less tan areas like this color and this color, and moderate are this. And what we can see is that it looks like from stream flow, there's a lot of drought going on. The rivers are really low in a big portion of Kansas. However, the precipitation is not that abnormally low. And we have a series of years here, chunks of years that are on the graph in Kansas first. So we have the time when the Dust Bowl it was definitely lower than normal. And maybe precipitation now from 2000 to 2006 is slightly lower than normal. But the drought in the 50s was really low, right? And then the years in between that are pretty much the same as they have been from the 60s to 2006. And then there's examples of different rivers for those different chunks of time period on the right, where the y-axis is the discharge and the x-axis is each of these sections of years. Well, we can see during the Dust Bowl, the Republican River, which is the one one of the two that the Republican and the Smoky Hill are the two that feed in to produce the Kansas River, right? The Republican River was pretty high median, pretty high flow. The Solomon River was pretty high flow relative to some of the other years, as were the Solomon, and the Smoky Hill was a little bit lower than some of the other years. But in essentially all these cases, the lowest is the year from 2000 to 2006. So even though precipitation was normal, the water flow levels, the discharge was much lower. This is why why you would predict there was actually a drought going on from the stream flow. But the reality is that the precipitation was normal. So what is it that's causing this to occur? And we talked about it in the last slide or two.
Was it lower water table?
Right. It's basically abstraction of water, of groundwater. Now, as I mentioned, many of these areas aren't in the over the Ogallala Aquifer, but there are other aquifers, and there's a lot of center pivot agriculture, and it is just basically drawing the level of the water down. This is then leading in turn to extirpation or extinction of some species of fishes that depend upon the streams, particularly in western Kansas, because historically, even during the Dust Bowl, you see here, there was discharge, right? So these fishes had a place to go. But when it gets really dry like this, then the rivers get fragmented. And there are particular species like the ones that broadcast spawn, that release their eggs, and they have to be in the water column going downstream before the larvae can hatch out of them. And they need turbulence. So if it stops or it's slow, they just sink out, and then they'll get in the bottom and not be able to complete their development. So this is leading to actual biological effects, in addition to limiting water for different communities and surface water for agriculture.
So can you repeat, just it's all back to intensive farming, overusing water in farming?
Exactly.